In our previous few videos, we have seen how sequencing distillation column can save energy and how simple operational improvements can also make energy efficient distillation systems and saving in the energy. In today's video, we are going to see how can we integrate distillation column with other process and how can we utilize the pinch analysis in order to save energy in distillation systems. So if we have a process wherein there are few hot and few cold streams and we convert them into a cascade of energy wherein you have different temperature intervals starting from interval 1 to 2 to 3 to 4 to 5, and we analyze all those process streams using problem table algorithm, and we find out the minimum amount of hot utility and minimum amount of cold utility using problem table algorithm, which we already discussed in one of the earlier videos. So we find out the requirement of minimum hot and minimum cold utility for given set of a problem where we have hot and cold streams. If you look at this, for every interval there is transfer of energy. So from QH to Q1 there is a transfer of energy which is of the amount delta H1. Q1 to Q2 there is delta H2. Likewise, from QH to QC at every interval we pass on some amount of energy. None of these energy transfer values is negative, and the value of the energy where it is zero is termed as a pinch point. Anything about pinch point in terms of temperature is above pinch region, and anything below is called below pinch region. Above pinch region is known as sink and below pinch is source. That means above pinch we receive the energy in terms of minimum hot utility. Below pinch we release the energy in the form of minimum QC, that is minimum cold utility. So this is something which we are doing for pinch analysis. So for a given set of problems, we generate this kind of information. When we club this information with distillation column and try to exchange energy between this process and the corresponding distillation column, we call it as a integration of distillation column with the process with the help of pinch technology. Just like we have analyzed the energy flow of a process in terms of PTA, let us see the energy flow of a distillation column. So if I want to represent a distillation column on a TH or TQ diagram, this is your distillation column. Now distillation column in terms of energy can be represented by this. So this is an energy balance equation where FHF is the enthalpy going into the distillation column through feed. DHD and BHB are the energy which is going away from the distillation column through distillates and bottom, and Q reboiler and Q condenser are correspondingly the heat duty associated with reboiler and condenser. Now if we say that these two are latent heat and these are sensible heat, right, we can say that for all practical purpose FHF equals DHD plus BHB, which is they are more or less same, or in other words we can say that reboiler duty and condenser duty would be more or less same, and a distillation column can be represented only by this because this being very high in terms of amount compared to this sensible heat. So we can say the distillation column in terms of energy can be qualitatively represented by the energy associated with reboiler and that of temperature, and since these are latent heat the temperature is not changing with change in energy. So this is your condenser duty, this is your reboiler duty, and this is your distillation column from on TQ diagram. So this is at the condenser temperature, this is at the reboiler temperature, and we can represent the distillation column through this box. So a distillation column can be shown as a rectangular box on a TQ diagram scale. So now if I put a distillation column along with a process, right, I'll try to integrate that. Now heat integration characteristics associated with distillation, as we discussed in the previous slides, some of the things would be repeated, is that dominant heating and cooling utilities are associated with condenser and reboiler. Heat to the reboiler must be supplied at a temperature above the dew point of the vapor leaving the reboiler, and heat to be removed from the condenser must be removed at a temperature lower than the bubble point of the liquid. That means when we want to supply the energy utility to reboiler, it should have a temperature which is more than dew point, and when we want to remove energy from condenser, the temperature should be lower than the bubble point of the liquid. Both reboiling and condensing takes place at a range of temperature, but for all practical purpose, this process are assumed to take place at constant temperature. So that is how we are able to represent the distillation column as a box. Otherwise, the temperature might change. So this is a horizontal line which is representing it as a constant temperature. So now, on this diagram, which is a TQ diagram, you know, both the things are shown together. That is the process and the distillation column. The purple color box shown here on the right hand side is distillation column, and this yellow and light blue color zones are nothing but your process, which are similar to your energy cascade, which we discussed in the beginning of this particular video. So this is your heat sink where you receive the QH minimum. This is a pinch point and this is heat source and you release QC minimum. So this is for a process. Parallelly to the process, if I have a distillation column, in distillation column I have reboiler energy going here and condenser which is removing the energy from here. One thing which we must note is that the distillation column is overall, as far as flow sheet is concerned, is a part of the process. But when we want to analyze the heat integration, we separate the distillation column from the entire process. So a distillation column is treated separately, and all other process variables, process streams are considered in the process which is shown on the left hand side. So now what we try to do is we try to exchange energy between the process and the reboiler, and we try to check that how, with reference to the temperature of pinch and temperature of the distillate and bottom, is your distillation column should be placed so that we have benefit of exchanging energy. So right now distillation column is placed across across the pinch. How can I say that? Is because the reboiler temperature is more than the pinch temperature and condenser temperature is less than the pinch temperature. So the pinch point is coming between condenser and reboiler temperature, and hence it is called as the column is placed across the pinch. Now total amount of energy required here, if I consider process and boiling process and column separately, then I have required QH minimum and Q reboiler for a hot utility and QC minimum and Q condenser for the cold utility. If I try to exchange energy between them, so this is a total, right? So if I try to exchange energy between them, what I do is I supply this Q reboiler from the process to distillation column, and I give away the condenser duty to the process. So overall, if I look at this process, right, it receives some amount of energy, like it releases some amount of energy, gives it to the distillation column, and it gives back the energy to the process. However, what happens is that the reboiler duty of distillation column is shifted to the process, and condenser duty is also shifted to the process. So overall, if you look, there is no change in the amount of energy of the process, because Q reboiler and Q condenser are having the very similar magnitude. What happens in this case is that the total energy which was required first for column and process separately was QH minimum plus Q reboiler and QC minimum plus Q condenser is now shifted entirely to the process, where the process requirement becomes QH minimum plus Q reboiler and QC minimum plus Q condenser. The distillation requirement goes away, right? But what I'm doing here is I'm exchanging the heat across the pinch. If you look at this diagram, right, I'm removing Q reboiler amount of heat from sink Now this is a process sink. This cannot act as a source, whereas in this case it is acting as a source. In order to make out that, what happens is I have to add Q boiler here, which is eventually added to QH minimum. So I need to supply Curie boiler amount of heat to the process, which earlier I used to supply to the distillation column. So as such, there is no change in the utility, either hot or cold utility. But another problem here is that earlier my reboiler duty I was supplying at this temperature. Now I am supplying it at a higher temperature. So in fact, I need to use a costlier utility compared to the utility which I would have used directly in distillation column. So placing a distillation column across the pinch is not going to help me, right? Because whenever I transfer heat across the pinch, it's going to impact the overall process only. So integrating a distillation column across the pinch will not serve any purpose. Other possibility is that my distillation column is above pinch or below pinch. Above pinch means my distillation column temperatures are both greater than pinch point. So my pinch point temperature is this. This is my condenser temperature. This is my reboiler temperature. Now in this case, what happens is that I remove energy from above pinch area, supply it to the reboiler, and the column itself provides that condenser duty back to the process above pinch only. So if I make the energy balance here above pinch, it is QH minimum plus Q reboiler, because when I remove Q reboiler from process, I have to add that amount to the process, but Q condenser comes back to the process, and since we know that Q reboiler and Q condenser are more or less of the same magnitude, the difference between Q reboiler and Q condenser is almost zero, and hence overall, if I see, then total is, without integration, is QH minimum plus Q reboiler, right, which was earlier the case. Now it is QH minimum plus Q reboiler minus Q condenser. So my entire distillation column is served from the process itself, and there is no addition of energy, right? And earlier, if there is two separate things, that is process and column, I require QC minimum and Q condenser. But in newer case, after the integration, I only require QC minimum. So basically, I require only QH minimum and QC minimum for both reboiler and the both distillation column and the process itself. So integrating distillation column above pinch will certainly help me save energy, and in the same way I can save energy when I can integrate the distillation column below pinch area. In the below pinch region, I have to supply only QH minimum in top and QC minimum plus Q condenser minus Q reboiler. Eventually, Q condenser and Q reboiler being same, my addition to the QC minimum is almost zero, and hence I am able to save energy while I integrate the column. So proper placement of a distillation column is either above or below the pinch. Across the pinch, if I put a column, then I will have issues in terms of saving energy. So we'll discuss this in detail, like with the energy intervals, when we meet in the next video.